Welcome back to our statistics learning session. Today, I'll be talking about Bernoulli experiment. It's a worked out example. Before we do that, let's quickly review what we discussed in our last lecture about type 1 and type 2 error. Type 2 and type 2 error are those errors that happen when when we conclude something different than what really is. Let me draw a grid so that it will be easier to understand what those are. This is a grid where it has different cells. This is H0, this is H1. These are hypotheses from test. This is theta naught and this is theta 1. This is truth. Secondly, we have our test 0. Test produces 1. This produces null hypothesis, this produces alternate hypothesis. Okay. So we have this. When the fact is when the fact produces is when the in fact the data says is in theta naught, but the test says it is false, then we are in right side of the facts. Secondly, when data says when the fact is if the fact is theta 1 and the test says it is true, then we are on the right side of the facts. But when the data is theta 1 but test says 0 or false, then we have missed the discovery. Hence, it is a type 2 error. Type 2 error. And when data is in theta naught, but our test says true, then we have false discovery, which is type 1 error. In this way, we have these 4 situations, and out of 4 situations, 2 of the situations are error. The probability of making a type 1 error is defined by alpha. When we talk about type 1 error, we really are talking about null hypothesis. That is, we are talking about theta naught. We really want the theta to be in theta naught to make a type 1 error. It is obvious from the fact and by looking at this grid. And let's say this is theta naught and this is theta. These are two different sets. They don't overlap. And each of the values in theta naught have probability of making type 1 error. That is theta naught. Out of all those values or probabilities, what is the maximum or what is the supremum or maximum value? That value from theta naught should be less or equal to should be equal to should be less or equal to certain level, and that level is called alpha of the test, alpha level of the test. That is, if I look at all the possible mistakes probably it can make, the super or maximum value should be equal to alpha. Now what happens in this case if there's only one, probably one only possibility of theta? Let's say I have theta is the only one singleton, and it's the only one possibility, which is half. Then you can say that alpha of half, one and a half is equal to alpha, because there's only one possibility, right? There's no other possibility of theta not. It's a singleton value. That's why you can say like that. Now we have talked about these alpha and type 1, type 2 error. Let's focus on Bernoulli experiment. Bernoulli experiment is where there are random variables x1 through xn. They are independent and identically distributed according to probability p, and probability p lies within somewhere between 0 and 1. For this we have two hypotheses. Null hypothesis is p, the probability of each of this common distribution of this Bernoulli is half, one half, and alternate hypothesis is it is not equal to one half. These are null and alternate hypotheses. From looking at the data, we can give a best case that what the value of p is, and this is usually xn, or sample average, is equal to p. This is our best case for this one. Now we have our hypothesis. Second step is to create a test statistics, a, a statistics for test. How do you do that? Let me show you. First, we'll start with p n, which is maximum likelihood estimator of p, which is xn in our case, and the variance will divide by p1 minus p, which is the actual or true value of p, and square root. This is our test statistics. And we are putting absolute here because it is two-sided hypothesis or two-sided experiment. That's why we are putting absolute here. Besides that fact, when this goes to infinity, then it converges to standard normal. Now we have our test statistics, and it gives us some value, Tn. If value of Tn is too large, then we can conclude that it is not equal to one half, and the value of Tn is too small, then we can conclude that it is equal to one half. The key thing here is that we have to control the alpha level of our test statistics, and we can only do that when it is under the null hypothesis. If it is not under null hypothesis, then we cannot control alpha. Alpha can be only controlled under null hypothesis, which is equal to fair or not. And for other hypothesis, the type 2, we'll cross our finger really hard and hope that it works out in our favor. The easy way to control alpha is to never reject anything. We'll accept we'll always accept null hypothesis, but that's not ideal. We'll never discover anything if we do that. Then how do we control alpha? Let us let's try to understand how do we do that. First of all, let's imagine that we are we have this out test and we have our maximum likelihood estimator of the p, and we have our p. We'll just copy test statistics here, and probability, let's assume that if it if it this the value of this, if this is certain, let's say some set r, and then we have to reject that, then the probability of having this kind of situation, let it be equal to probability of alpha of p, which is usually 5%. Let's just imagine that for a second. Then under null hypothesis, we can say that, but we can only consider this under null hypothesis. And under null hypothesis, the not null hypothesis is always when the value of p is in fair or not. And what is fair or not here? The value of p is always in fair or not. And fair or not is a singleton where it is 1/2. Then, if that is the case, then this p, you can replace p with 1/2 and n with p naught half and 1/2 equal to r, which is still equal to p 1/2. We can say that, can't we? Yes, we can, because that's the simplest way to explain this. So this is how I build my test. Now let's talk about the rejection region, which makes sense. We have our test with some probability of alpha, which is 5%, but we still have to define our rejection region. How do we do that? Our test, which is this, rejection region is where this alpha n, pn, and half is equal to half is greater than some value. Let's for now say if the value is c. If it's greater than, if the absolute value of this is greater than value c, then we're going to reject and say that this probably alternate hypothesis is true. Just a side note, we are taking absolute value because this is a two-sided hypothesis. or this is a two-sided test. Now, focusing on coming back to our main point, if it is greater than C, then we will reject it, and that's how we define our rejection region. At the same time, what we can say is that I want the probability of rejecting the same rejection region. Let me do this. The probability of rejecting we still we still want that be to be alpha. It is still true. This fact is still true. This fact is still true. We still want that to be alpha, but we can say that only when it is at asymptotic level. We cannot do that in normal level, but we can only say this in asymptotic level. That is, p half n p n half is greater than some c only at asymptotic level. And how do we define c here? C here becomes q alpha half because it is two-sided test. Now we're gonna express the rejection region in a different form. The simplest form of rejection region is to say that rejection region is where the values of my data I reject. That means rejection region for test is our Tn is greater than q half. That means when my test reject for all the data points for my where my test is rejected or test fails, that is my rejection region. It is kind of pedantic, but that's a fact here. I'm rewriting rejection region in terms of our test statistics, and this will be always at asymptotic level, which means at infinity level. Let's let's I want to add a few points here. The few points are those that we are doing Bernoulli experiment here, and in Bernoulli experiment I am using the value p, which is equal to half under null hypothesis. And this kind of formalism, which I described here, gives us really advantage because using just one value of p, I am describing mean as well as variance. That helps to define the test at asymptotic level or infinite level, which also use the central limit theorem. And hence, this is a definitely a way to do the testing for A/B testing. Let me quickly summarize what we discussed today. We started with a quick review of type 1 and type 2 error. Then we talked about type 1 error in a little bit detail and why it is supremum of error not. Secondly, we dig deeper into Bernoulli distribution and define the test statistics for Bernoulli distribution. And we also talked about the rejection region for test statistics and how it is related to the probability, or how it is related to type 1 error. And then we redefine our rejection region in terms of other test statistics. That's all we did today. Thank you so much for listening. I will see you in next learning session. Thank you so much.